Hello and welcome back to differential equations. This is section 5.3 on a little survey on, it's a survey of solutions, solution curves for linear systems. Now, let's first see what it means to have this section at all. Solution, right, evolved as you learned mathematics. The first solution you ever learned was solution to equation, let's say x plus, dramatic, x plus 3 equals to 5, and then x equals to 2. And that is just going to be number 2 on the number line. The next type of a solution was, let's say, x minus 4 equals to less or equal, let's say, then 3, and then you used to draw at 7, and like that, right? Shading all of this, saying, that was my solution. And you had the systems of two equations, for instance, and the solution was an intersection point between two linear equations. So I don't know, x plus y equals to 3 and x minus y equals to 4. So this one is y equals negative plus 3. So let's say this is where 3 is. So this one would go like this. And the other one is what? Y x plus... No, this was a negative x. It will go the other way. It will go this way, right? Because there was negative x, and this one is y equals x minus 4. So we'll go like this. This one has to go through here. So they will intersect there. And that would be a solution. XY point, and so on. So this is old, right? Any type of equation that you had, whether it was exponential equation, logarithmic equation, any type of equation would give you these solutions. And then eventually, right, going through exponential, logarithmic, trigonometric, all gave numbers or 2D points if you were intersecting. Let's say you intersect parabola and a circle, and it, 2D points. Now 2D point is right there. Or let's say you have a circle and you have a parabola, and then it gives you these two as solutions. So this is the evolution of your solutions, and it's always a number, whether it's a one-dimensional number or point in space, which you can call a two-dimensional number, just like a complex number is a two-dimensional number. And then you entered in the world of nu, which was differential equation. And in this world of differential equations, your solutions became functions. So now, what we had is that first initial problem, dp dt was equal to kp, whose solution was p of t equals p0 e to the kt, and then the solution was exponential function graph with a p0 right there. So the solution was the entire linear function. So not linear, exponential in this case. The entire exponential function was the solution to the problem, and we are expecting, right, to see different solutions as functions, and then those solutions become, you can draw those solutions, so on. Now, some solutions are explicit, some solutions are implicit, ones where you can't separate. So this was explicit solution, and you can have also implicit solution. So a graph like, let's say, graph like that on the xy plane, that will be implicit solution, because you cannot separate. See, over here you have your function equals everything else, right? Where your dependent variable y. So for explicit solution you can write y equals f of t. For implicit solution you can't. You can just have f of t y equals to 0 or a constant. So that's for implicit solution. And then we also covered the slope fields. And the slope fields gave us a possibility to solve differential equations by figuring out what the graph looks like rather than actually computing the functions. So we would draw those isoclines and we would figure out, we'll put those little slopes on every isocline, and then we would, what I said, snake the solution through. So now we want to see what, and we should be familiar with these things, right, from our pre-calculus course and then calculus 3 course, right, how to draw all of these solutions that I've mentioned so far. Now today's lecture is going to present what the solutions look like, the gallery of solutions for linear systems, and we are going to focus on systems of dimension 2, right? So that's when we have systems of 2 differential equations. Which is, the meaning of this is dimension is n equals 2. So, when you are dealing with the systems of dimension 2, we are talking about our good old system A prime equals matrix A of coefficients times x, which was solved by vector x equals vector v times e to the lambda t. And you can have any number of variables in here, but we are focusing on 2. But if you want to have 17 equations, you can have 17 equations. This would be your 17 by 17 matrix. So we don't want that. And we were able to write the solution as C1 V1 e to the lambda 1 t plus C2 V2 e to the lambda 2 t all the way to Cn, right? Depending on how many of these you had. Lambda fit. Okay, good. So all of that stuff that we did before, there is nothing new. We learned all of this in 5.1 and 5.2. So 100% of what I circled there, boxed there, was equal to that. We also learned now for a dimension 2 that for our x prime ax, right, this is going to be 2 by 2, and we are going to have our solutions given by x of t is going to be C1 V1 e to the lambda 1 t plus C2 V2 e to the lambda 2 t. So that's if the lambdas are real, and if lambdas are complex, we can have the system given by, so C1 e to the pt. I'm copying the same one from the book. We used a little bit different form earlier. Cosine qt minus b sine qt. We used a and b in the beginning, but now we have to have all of the other components because now a and b are our vectors, so it gets to be a little bit confusing with the notation. Cosine qt plus a sine qt. So that is if the solutions were complex. And we also have one more for repeated eigenvalues. So C1 V1 e to the lambda t plus C2 V1 t plus V2 e to the lambda t. So again, remember how we used to multiply by x? We used to multiply by was it in chapter 3? We multiply for the repeated solution. We multiply by x, multiply by t. Well, there's nothing new. It's all the same, right? So we have real, repeated, and the complex. So the same 1, 2, 3 case, right? In this case, 1, 3, 2 that we learned in chapter 3, we have the same for our linear systems. And now we will divide the cases into, so we have real, complex, and this one, which breaks into a lot of different cases, but it's more of understanding what type of a solution it's going to get you, so that you don't actually have to solve all. You know that something that you need differential equations to model, something might fail because you just know what the solution to that differential equation is, and that might not be desired outcome, and you would just say, well, I don't want this, right? So you don't even pursue solving it all the way, because you just know what the solution is going to work for. Let me just give you a very basic example. If you want to create a battery, and then there is some kind of differential system that you have to solve, and you see that differential system is not going to be radiating the energy out, which is what battery is supposed to do, clearly you're not designing a battery, right? So something that you, right? So these things are for designing. They're not for I don't need to know this because I'll be pressing the button. Exactly. You don't need to know this if it's pressing the button. Someone had to design the system so that button exists, right? When you are taking advanced engineering courses, and if you are going to be working on a design, yes, you need to know to do these things, because you need to be designing the right things. All right, so let's talk about real eigenvalues. So we can even label this 1, 2, 3, right? And then number 1, real eigenvalues. And well, actually they mushed these together. So this is like case 1, case 2, and this is case 1, case 1a. Whatever. So real plus repeated. Real eigenvalues and repeated. There we go. So both of them in the same. And we have categories for these. So the real eigenvalues, so distinct, versus repeated. Need more room. All right. So what are the possibilities? Non-zero of opposite side. Non-zero of opposite sign. Lambda 1 is equal to 3. Lambda 2 is equal to negative 4. Right? Non-zero of opposite sign. So you are looking for numbers that fit the categories that are given to us. So see, you just find lambda, and you already know what type of a solution you're going to get. You don't know exactly where to graph it, but you know what shape. We'll see that. So both negative, both positive. Both negative, both positive. And then 1, 0, 1 negative, 1, 0, 1 negative, and 1, 0, 1 positive. So each one of these will have their own type of a graph. And then we have for repeated, right? You can have 2 positive repeated. So lambda 1 equals lambda 2 equals 3. And then both negative, and then both 0. So those are easy because it's repeated. So both positive, both negative, and both 0. Right, so that's it. So these are all the cases for real eigenvalues, and we just need to run through what the pictures, right, what the solutions would look like, meaning which way the solution goes. Now, when I say which way the solution goes, that means that you will be following along with the line to the graph of the function. So let's see our start with the saddle points. So the solution is given by C1 V1 E lambda 1 T plus C2 V2 E lambda 2 T. So what is the verdict? Now, if you remember vectors V, those of you who took basic physics, took Calc 3, took linear algebra, you know what the vectors are. And when you have the solution over here, you can see two vectors in it. You can graph those two vectors. So if I draw the XY coordinate plane, and then I draw two of these vectors, so call that vector V1 and call that vector V2. Right? These vectors have finite length. Their directions will create, there we go, something like that. And this is where we encounter the graphs that will follow these curves. So you will have a solution that follows this curve, bends, and follow this way. And then follows that one, goes there, follows this one from here, goes this way, and on the other one follows this one, goes that way. There we go. And this is what is happening when you have your solutions of lambda being of opposite signs. So both real and non-zero, and so real, non-zero, opposite sign. So the orange are your solutions, right? And you see a lot of curves here, right? Is this a function? Well, remember, your solution to differential equation is not necessarily a function, right? Because you can have explicit, if you remember, you can have implicit solution. You see, remember it? That's not a function, but it's a solution to a differential equation, right? So how many of these? And then when you have a critical point or initial point given, when you have initial point given, you can eliminate some of the lines. So a saddle point, right, would be the one where you have this type of situation where the solutions go in. I'm trying to avoid Calc 3 because I know not all of you took Calc 3, right? The saddle point has values going into it and the values going out of it. So it's I'm just going to go and I'm going to go to the saddle point from calculus, and maybe it clears the situation on here. I mean, I don't have a lot of choice here. So yeah, if I draw a parabola that looks like this, opens downwards, it has a max point here. If I draw a parabola like this, it has a minimum point right there. Now, if you think of a horse saddle is parabola downwards to wrap around the horse. So the horse goes in here. But if you look at it from the 90-degree angle, right? So rotate 90. That's not R, that's S. You will only see this for the parabola now, because this is where the horse goes. And then there's going to be another parabola here, right? Because this is where you go. You go in a saddle. So the saddle is going to wrap around the horse and have a parabola that wraps the horse, but then there is going to be a parabola here in which you sit. There is this special point here that is a minimum and a maximum, right? There is a minimum and a maximum at the same time, depending which angle you're looking at, right? If you're looking sideways, that point is a minimum, right, for the parabola that you are sitting on. But if you are looking at forwards, right, if there is no horse, you're looking forwards at the saddle, you are seeing the parabola that wraps around the horse, and that parabola has a maximum. So the same point, that's why it's called a saddle point. The same point is the min and a max at the same time. And because it's a min and a max at the same time, you have the point. I just noticed the mistake over here that I put x and y instead of x1 and x2, which are solutions. And all right. So this, in this case here, right, for the saddle point, you this point, the red point, is the min and the max at the same time. So here, if you look at my point in the middle of the graph, right, which is called the saddle point, I hope you see that these are running away as these are running in. Do we see in that general motion there? Right? So you can see that this is not, it is absorbing and radiating at the same time. I hope this terminology would somewhat help. Absorbing and radiating. I don't know what else to say. All right, cool. So that will be the saddle point. And now that you understand the radiating and you are understanding the shining out that's radiating, then you can also now have all of them going in and all of them going out. In which case, they are called sink if everything is going in, right? Or a source if everything is going out. Sun is the source of energy, right? It radiates radiation, right, which hits our atmosphere, and greenhouse effect makes it warm. There is no direct exchange of temperature between sun and earth. Heat doesn't travel through vacuum. It's okay to park your spaceship next to the sun as long as you are properly shielded against the immense radiation it gives out, but you are not going to burn because of the heat. It doesn't travel through vacuum heat. That's why the space is cold, right? Otherwise, it would be very warm if the heat was transferred through the right. If the heat was transferred through vacuum, so sun would radiate the radiation which hits, right? X-rays are hitting the atmosphere and then heating the atmosphere of the planet and makes it warm for us. All right, so the next one is going to be the sinkhole, right? With a sink where you have again these two vectors, but they are now going in and they're both negative, right? So we'll have now sink and we are going to have, again, you can draw any two vectors. These are your solutions x1 and x2, and you will draw again two vectors. You can draw any vectors you want. It doesn't matter what is the, right? These are all approximate anywhere. So call them v1, v2, and now they are all going in from different directions. So they're going in to fall into, right? And they're going in, and they're going in from the this one. All right, good. So all of these, so eigenvalues are non-negative and they are, non-zero and negative. Lambdas, non-zero, both negative. So this would be something that absorbs energy, let's say, right? Absorbs energy, and then you can have one that is a source which will radiate energy, and those are the positive ones. So we'll call that the source. Again, draw any type of these solutions. So technically most of your homework here would be to recognize the correct picture, right? To know what you are looking for. So here is one of my eigenvectors. Here's another one. These are arbitrary now because we are drawing these, and now this is supposed to be a source, which means the solutions will, I'm doing the air quotation marks right now, radiates out, right? So it goes wee like that. So the solutions will go out. So lambdas are non-zero and positive. Oh, I didn't say distinct. I have to say distinct as well. They're not repeated. They're distinct. So they're moving in. And then we get to the situation where we do have one of them to be zero and one of them to be positive, one of them to be negative. So negative and positive. Well, sorry, negative and zero, and then positive and zero. So lambda equals 0, lambda 1, let's say. I want to follow what they do in the book, so I have to do this, and lambda 2 equal to 0, let's say. So now 1 lambda is negative and 1 lambda is 0. Again, they're both real, right? Because I don't see any complex numbers there. They're both real. They're clearly distinct because one number is 0, the other one is negative number. Now these solution curves will be parallel. So we're going to get straight lines in this case, and they will be parallel to the vector v1, and the vector v1 is the non-zero vector. So the vector v1 is in eigenpair with the non-zero lambda. So when I draw the solution, and we come up with, two, again, whatever we put, we just need to be careful that we are parallel with our solutions with the v1 vector. So whatever you put down for v1, make sure that you are parallel to v1. So if this is my v1 vector and this is my v2 vector, my solution curves will be parallel to v1, but both going towards v2. So parallel to v1, parallel to v1. There we go. So this is what the solution curves would look like. They're moving in towards the v2. Again, where these are depends on your C1 and C2 constants if you have initial point, because they have to go through certain values, right, on the XY graph. And the positive one is going to go outside. Can I save? Yeah, I can save a picture. I'll just do blue and say lambda 2 is still 0. So lambda 1 larger than 0, lambda 2 equal to 0. Same situation, and I'm just going to recycle the same graph. So you follow the orange one for orange and the blue one for blue one. So that takes care of those situations. All right, so that's the first 5 from here for the distinct. We covered all of the possibilities for the distinct eigenvalues. The saddle point was the non-zero of opposite sign, and then we had both negative, right, the sink, the both positive, it's the source, and then we had these straight line solutions that were going towards the 0 eigenvalue vector, or are going away from it, right, depending on whether the non-zero eigenvalue was positive or negative. Now, the repeated eigenvalues, both positive and both negative, they are going to go in as a, I think it was called a proper source, and I think just gonna really quickly look into it. Proper and improper, yeah. So again, this is going to be the source for the positive, and it's going to go out straight, or it's going to go out in a in a kind of wavy fashion, because you can also have, so both positive, both negative. Let's take a look at repeated. Repeated eigenvalues. So if you have a repeated eigenvalue, you will have the situation where they are going out just 1 second, I have to verify before one thing. Yeah, the independent eigenvectors. So these have more cases. So when you have repeated lambdas, you can have dependent and independent eigen. That's now branching into too much. So you can have a solution that has two different eigenvectors, and you can have a solution with a single, repeated eigenvector. So they will give you both solutions that go in, but you will have a solution that goes in like this, right, as it goes in as a sink, right? And then the other one says, instead of having the blue ones, it goes in a whatever, something like that, right? And goes in like this, but they're all going to sink into the same place. And the 0 ones are going to be parallel to the V2 vector. V1 vector passing in opposite directions. But generally, this case is not a case that we generally use. Repeated eigenvalues, I wouldn't even worry about it. The most important case that most of you have to worry about is the complex case. That's the more important. So you have the sink, you have the source for distinct, and the complex cases. Complex cases are, even though I teach this, I tend to forget the repeated ones because they are very rarely around. The most important cases are obviously complex cases because most of the systems are oscillation systems. When you talk about the spring, when you're talking mechanical systems, when you're talking about pendulum and spring and all that stuff, and then when you're talking about electronics, and you're using alternating currents, which is technically everything we do except stuff that runs on batteries. Even that is converted into alternating in some cases. We have a lot of oscillation in our radio waves and everything else that's oscillating. That's all complex solutions. Anytime you have waves, it's going to be complex solution, and that includes optic and sound and earthquakes and technically everything. So for mechanical engineers, it's going to be oscillation. For electrical engineers, it's going to be oscillation. So we're having a lot of complex answers, and those solutions are the most important ones that we get. And I think they give us a really nice survey on page 315 and page 316. If you go to that one, they really summarize all of them nicely. Now I'm going to just mention the complex solutions and we are done. This is just a gallery, a survey. We know how to solve these equations. We just need to see what the solutions look like, because we are going to have now multiple solutions. Now you want to go to three, right? Three equations is going to be a three-dimensional graphs and so on. So just want to go into complex and solutions. No, complex eigenvalues. And you see me writing this in red because you are most likely to run into these ones in your later coursework when you move on to the four-year school, right? You are going to see these ones most of the time. So pure imaginary lambdas. So that means no real part. Some of you will go, duh, but hey, we're not all dealing with complex numbers all day long. No real part. So you have lambda equals 4i, that's it, right? Then you have something that is called a center. The solution will just hover, whether it's going to be a circle, an ellipse, or ellipse, sideways ellipse, or so on. So all of those are possible. So you are going to have, depends on your solution. The book only gives one. It's enough to understand that if you have ellipse like this, right, then all of the other ones, and then you pick, then you will have initial point to tell you which one of these to pick. But it can be a circle, because circle is a special ellipse where the two small radius and a large radius for the ellipse, which were labeled as A and B, they are both R. So you have it for a circle, right? So that's the case. And then we have complex eigenvalues with positive and with negative real part. So this is complex eigenvalue real part larger than 0. And if that is the case, we know that the complex is going to make it to go in an elliptical motion, but the positive part will make it go away from the center, which creates a spiral. So spiral motion. So it's going to go like that, and it's going outwards. So this is going to be called spiral source, right? And complex, last case, complex eigenvalue real part less than 0, it's, should I say clearly, going to spiral in. I'm still going to draw from the center, but I'm going to flip my arrow, right, going inwards, right, and that's going to be called spiral sink. So you have a system, right, which oscillates. So these are the two springs connected, right? You have two inductors, two loops connected, and one of the systems with a positive eigenvalue is going to spiral out, if you remember the resonance and all that stuff, right? Adding energy, and the other one is going to spiral in into the sink and stop, right? Now I just hope that you understand that stuff is not supposed to spiral out. So this is why we are learning the solutions. You want the stuff spiraling out if it's oscillating from the sun, so it gives us energy, but you don't want that in your battery design. You don't want that into, in certain cases where it's not good to have radiation of energy out. Sometimes you want to contain the energy, and certain systems you definitely want to stop after some time. So that's something that you need to keep in mind. So most of your homework should be you solve for your eigenvalues and you just match it to one of the pictures, and that's it. Now we do have a next section to be second order systems and mechanical applications, which is mechanical engineering, right? For with eigenvalues. So you have a couple of them put together that gives us a system, and so on. And unfortunately there is no electrical one, so those systems tend to have more components, and their solutions get to be way more tedious than two springs connected to each other with the two masses. So I hope you guys found the syllabus, the new syllabus I posted on Canvas, and you have carefully read the new assignments and new grading procedure and so on. You will have option to choose pass no credit this semester because of the virus outbreak. And it's clearly explained in the syllabus what it means. So if you, I'm just going to give an example with two grades. If you score C, you can keep C, and you can calculate, and then you will be calculating that C into your GPA because you kept C as a final grade for the course. If you earn a C and you pick pass no credit, you still pass the course because you passed it with a C, but that C will not be calculated in a GPA. So that's the difference between keeping the C or replacing C with the pass P grade. If you scored C in a class and chose pass no credit, then no change on the GPA. You can graduate. You can take next course if there was differential equation. If we had partial differential equations, you would be allowed to move on. Now, grade D. Grade D is tricky because with the grade D you can graduate, you can't transfer. So you can choose pass option, right? But if there was partial differential equations, you will not be able to move on until you retake differential equations. So if you are taking, I don't know, German 1 right now, and you pick D, and D is not going to advance you to German 2, right? German 2 would require C or better, you have D. Now, even if you pick pass, it's still D, so it still doesn't advance you. You have to be careful about that stuff. In general, D's don't transfer, so it's something that this no credit thing is in place, so your GPA is not impacted. That's it. You still have to work hard and pass the course, I've noticed some confusion with students where they say, oh, if I score D or F, I'm just going to say pass, no credit, and then I can move to the next class. With D and F, you cannot move to the next class. It's D, it's F. The no credit thing is just, I am not ruining my GPA with the grade that I probably would do better with if I was in a regular class rather than this online nonsense. So that's the part. Please read the syllabus. Make sure you go through all of the policies there. I added an assignment to have the course stay transferable. I had to take away the project, and if you have any questions, we'll deal with that in the office hours. So I will catch you all guys tomorrow, right? We'll have a little bit of mechanical, right? And then we might jump onto the next section, right? So we're going to do some of the mechanical and then talk about multiple eigenvalues 5. So maybe we take care of this. Exam 2 will feature chapter 4 and 5. So the sooner we are done with chapter 5, we'll go into chapter 7. We'll skip 6. We'll jump into very important stuff, chapter 7, and then we'll see what time we get until, because there are only 3 weeks left. All right, bye.